back at AP Review. This is 2014 AB BC Free Response 4. Train A, oh, that's a bad sign. That probably means there's a train B. Train A runs back and forth on an east-west section of railroad track. Train A's velocity, measured in meters per minute, is given by the differentiable function v sub A of t, where time t is measured in minutes. Selected values of v sub A of t are given in this table. Okay, so before we do anything else, number one, there's probably a train B. Number two, you're probably going to be asked to estimate the acceleration, because this is velocity, by finding the slope between 2 points on this table. And number three, you're probably going to be asked to estimate like total distance or displacement or something else by using an area approximation method on this table, right? LRAM, RRAM, trapezoidal, something like that. So knowing that those are the things that are going to happen when you look at a table problem with a fair amount of certainty is an easy way to calm down and say, whew, I know what to expect. They can only throw so many curveballs. So let's see how many curveballs they threw. Part A, find the average acceleration of the train A over the interval from 2 to 8. Well, that's nice of them. So they want the acceleration from 2 to 8, right? Remember that acceleration is the derivative of velocity, but average acceleration is just old school change in velocity over change in time. So that's basically what I told you about estimating acceleration, but they want the average acceleration. So that's going to be v of 8 minus v of 2 over 8 minus 2. Now be careful, because they did say the window from 2 to 8, and I think if you weren't paying attention, oh sorry, it's VA of 8 and VA of 2, my bad, there's probably another V later. So if you weren't paying enough attention, I think you could easily have done 0 to 12 without being careful about it. So that's a negative 120, right, minus a 100 over a 6, right? So that's a negative 220 over 6 in meters per minute squared. Now, if you want to cancel and make this a negative 110 over 3, by all means do, but if you don't, that answer is totally fine, right? Part B. Do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time t in the window from 5 to 8? Give a reason for your answer. Okay, so yes, and I'm going to walk you through why. Okay, so VA of t is differentiable. They told us that, which for the record means it's also continuous. So that, because you can't be differentiable unless you're continuous, right? Okay, we know that VA of 5 is greater than negative 100, and that VA of 8 is less than negative 100, right? So by the intermediate value theorem, VA of t equals negative 100 sometime in that window from 5 to 8, right? So again, the logic being, if you have a value that is, if you start, so your continuous function, right, v sub A is continuous because it's differentiable, and you do need to say that it's continuous. Since it starts out higher than negative 100 and ends lower than negative 100, right? 40 is bigger than negative 100, and negative 120 is less than negative 100. So by the intermediate value theorem, if you started above negative 100 and ended up below negative 100, you have to cross negative 100. So you needed to mention the intermediate value theorem. You need to mention that it applies because the function is continuous. And then you need to actually mention that VA of 5 and VA of 8 fall in the respective spots that they do relative to negative 100. Cool. Part C. At time t equals 2, train A's position is 300 meters east of the origin station. If the train is moving to the east, write an expression involving an integral that gives the position of train A in meters from the origin station at time t equals 12. Yep. Use a trapezoidal sum, there it is, with 3 subintervals indicated by the table to approximate the position of the train at t equals 12. Okay, cool. So let's walk through the stuff we know for part C. So for part C, we are told that the position, right, which I'm going to call XA for my, like, for lack of a better way to say it, right, I'm going to say position of A, XA, at 2 is 300 meters to the east of origin station. And if you picture the way never eat slimy worms, right, east would be positive 300, because east is generally considered to be positive. It's the positive x-axis. Okay, so here's what I know. I know that if I want position, right, so if I integrate from 2 to 12, of VA of t dt, I should get the position at 12, because remember that VA is like x prime A, right, or xa prime. So I should get XA of 12, which is the thing I want, minus XA of 2, which is the thing I know, right? So essentially, in order to find the position at 12, my position would be, I'd add this, the 300, right? Because this was a 300. I'd add the 300 over. It should be 300 plus the integral from 2 to 12 of VA of t dt. Now, you'll notice that my answer didn't use that x sub a or xa notation that I used. And the reason is because that's not the AP's notation, so I shouldn't use notation they didn't use. They actually did invent it and call it s sub a, which is fine. So I guess they would have been fine with me calling it x sub a, and that's fine. So this is the position I want, right? And if you want, you can actually, because the AP did seem to be fine with it, I can say that it's this. They used S sub A, it's fine. They didn't ever call position S, so as long as they didn't call position S, you don't have to call it that. Cool. So that's my expression, and now I'm asked to use a trapezoidal sum to approximate it. So it's going to be approximately that 300, which doesn't change anything. Now, I'm using a trapezoidal sum for this window. The way a trapezoidal sum works, right, the area of a trapezoid, and we're going to stand it on its side like this, right, it's got a height and it's got two bases, right? So in the window from 2 to 5, the height is going to be the 3 units from the 2 to 5, right? So I'm going to have, and remember, the area of a trapezoid is 1/2 the height times the sum of the bases. Because these heights are irregular, it's a 3 and then another 3 and then a 4. You can't use sort of a cheat calculus formula. You have to just find the height and find the area of each individual trapezoid. So 1/2, the first height is a 3, and the sum of the bases would be a 140. Plus the next trapezoid, the height is another 3, right? Because again, I'm going from 5 to 8 this time. That's 3 units. And then the sum of the bases would be a negative 80, right? And then the last one is 1/2. The height is now a 4 because I'm going from an 8 to a 12. And the sum of the bases should be a negative 270, right? So I'm going to get a 300 plus. Now, if I were you, I would use the 1/2 with the 40, right? I'd use the 140 and make that a 70, and I'd get that this is a 210, right? I'd do the same trick with the 1/2 and the 80. I'd make it a negative 40, right? So this is a negative 120. And then I do the same thing with the 4 and the half. I'd make it a 2, so that's a negative 540, right? Me personally, I'm probably going to put my positives together first. That's not that number at all. So I get a 510, and then I put all my negatives together, and my negatives seem to be a negative 660, right? So it seems to me that I end up getting a negative 150 as my position, and it was measured in meters, right? So I get a negative 150. And then they do ask, they didn't actually ask me to explain further than that. They just asked to write an expression and then approximate it. So essentially 150 miles meters, 150 meters west of the origin station, right? That's what that negative would indicate, 150 meters west of the origin station. And then finally we get to part D, and here comes train B. A second train, train B, travels north from the origin station. So now we have a train that's going north-south instead of east-west. At time t, the velocity of train B is given by an equation, which I'll write down in a sec. At time t equals 2, the train is 400 meters north of the station. Find the rate in meters per minute at which the distance between train A and B is changing at t equals 2. Okay, cool. I wanted to make sure how much I could erase, and I do still need the table, so I can't erase it. Okay, so here's what I know. I know, right? So I know that train B is traveling north from the origin station. So here's the origin station, and here's my train B, right? So this is B, right? And I know that train A, because it's at time is 2, when I know train A was 300 miles from the origin station to the east, train A is traveling this way, right? And so what they want me to know or find is the rate at which the distance between these two trains is changing, right? So I'm going to call that D for distance, right? So this is a related rates problem, right? This is a related rates problem. So we know that if I call this, I'm going to go ahead and call this Y and call this X because it already called the position for XA, X, right? So I have a diagram and I have rates, right? And I'm going to have to label them a little bit more clearly, but I know that this is changing at a rate and this is changing at a rate. Cool. So I need an equation that relates my diagram to my rates. Well, I know that it's Pythagorean theorem. X squared plus Y squared equals D squared, right? Now, what they want in this situation is they want the rate of change of d, right? So what they want in this problem, right, what they want is they want dd dt at the moment when t equals 2. But I know some stuff at t equals 2, right? I know that x, because this is technically xa, but I know xa of 2 was 300 because that was given to me, right? I know that x prime, or for lack of a better way to say it, I could even do dx a dt at t equals 2 is 100, right? I know the formula for the velocity of b, right? I know v b of t, right, which is the same as essentially my dy dt, right? It's the way that this quantity is changing, right? I know the formula for that, which is negative 5t squared plus 60t plus 25, right? So I could find dy dt pretty easily. I could find dy dt at the moment when t is 2, right? I could find that easily by just plugging in a 2, right? So that would end up being a negative 20 plus a 120 plus a 25. So that's a 125. So I now know dy dt. So I know dx dt, I know x, I know dy dt, and I can find y, and we'll talk through that in a sec. They tell us why. They say the train starts, they tell us that the y at that moment is 400 meters north of the station. So now what I want you to notice is if I derive this with respect to time, I get 2x dx dt plus 2y dy dt equals 2d dd dt, right? Well, I want dd dt, but I know all of these quantities now. I'm personally probably going to divide everybody by 2 just to make my life a little easier. But if I cancel out that 2, I get x dx dt, which are both numbers I know, plus y dy dt, which are both numbers I know, divided by a d should give me that value I want, dd dt. So now the only thing I'm missing is d, but the funny thing is that at this moment, right, at this very specific moment we're looking at, this is a 3, 4, 5 triangle. Because a is 300 units, right, and away, and b is 400, so this is 500. So I'm going to get, when I substitute in, that this is 300 times a 100 plus a 400 times a 125 over a 500. Now, if I were you, I'd cancel 100 out of everything. Like, I'd factor 100 out, and I'd make this a 3 times a 100 plus a 4 times a 125 all over a 5, because that's a lot easier. So I'm going to get that my dd dt is a 300 plus a 500 all over a 5, which should be 800 over 5, so 160 meters per minute. So that is how fast the distance is changing, 160 meters per minute. Now, that was a pretty tricky part D, I'm not going to lie. And I also feel like this train A travels and leaves the station, and train B, I think that's the stuff of math nightmares. But there you have it.